Today we're talking about work and energy at the beginning of the unit, and we're going to start right off with talking about kinetic energy, which is a particular type of energy. But to define energy is kind of a hard thing to do. Like, what is that? Especially since there are so many different types of energy. One definition I found was this one that says, like, the ability of an object to produce a change in itself. So you could maybe think about, I'm sort of thinking about like an object on the end of a bungee cord. You know, it might have energy stored in the stretch of the cord, and then when it returns to its unstretched state, it gains speed. So it goes back and forth between being stretched and unstretched, and that's a change in speed. So it'll slow down when it stretches and then speed up when it goes back to its unstretched state, or the world around it. So something that has energy, for instance, the hammer, if we say that has energy, as it swings down, it can cause the nail to go into the board. So energy is a scalar quantity, so it does not include direction. And again, we're talking about something that this object or system possesses at a moment of time. So the particular type of energy when we talk about kinetic is an energy associated with motion. And again, that's at a moment of time. Right now, how much kinetic energy is associated with that object or with that system. So we know that that's true, that moving objects do cause changes in the world around them, or they can, in the instance of like that bungee cord, cause a change in the stretch. So in that object itself. So we can imagine, a moving car can cause damage to your garage door if you run into it. A moving fan blade can move air molecules around it. This picture has water going over a dam, and that can be used to spin turbines, which produce electricity. That's what hydroelectric power is. So you can kind of fill in the blank there. What are you thinking about when you think about kinetic energy? And then we have a formula here that is on your formula sheet for the AP exam. Hold on, I'm going to grab mine and see where it is. Okay, so on your AP formula sheet, this is about not quite halfway down the left-hand side. Okay, when we talk about units, you should have seen this before, hopefully in another class, but we're using joules as the nickname for the mishmash of units, base units that you would use in the case of energy. You'll notice the difference here. I wrote what a Newton is. So they're only different by a meter. So you'll see the meters is squared in joules versus newtons. Joule was a guy who worked on the energy, like thermodynamics, thermal energy. Okay. All right. So let's talk now about how does something get kinetic energy, okay? Well, when we talk about that, we know that in order to accelerate, because we know that velocity's in that equation, 1/2 mv squared. So in order to gain velocity, something had to exert a force on an object, okay? So the outside world had to put a force on that object and give it kinetic energy. And so when we talk about that interaction with the outside world, we will call that work. And that, so we're using like a regular colloquial English word to describe that, which is kind of odd, but that's the idea here. Is that any transfer of energy to or from the outside world is known as work. And so if energy is transferred from the environment to the system, we say that positive work is done on the system. If the system transfers energy to the environment, okay? So if that car crash, if you hit your garage door, okay, with your car, then, the garage door might vibrate. You might put a dent in it, okay? And your car is going to slow down. So you're going to lose the kinetic energy. And so that's going to, we're going to say that negative work was done on the car. Well, probably a better way to say that is that the kinetic energy from your car was transferred out of the system, out of your car to something else. Okay, so then we're going to talk about some of these in class, but I think probably the best analogy in this list is the one I want to talk about in the video, and that is the money analogy. It's the most commonly used one. It's the one your book uses. So if energy is represented by the amount of money in your bank account, okay, then work, right, can be positive or negative, and it would be deposits or withdrawals. It's the process of how that amount changes. Because the amount of money in your bank account right now, that's a state. How much do you have right now? That's exactly what energy is. It's an amount that can change. And then the process of changing that is what work is about. And it can be a positive or a negative change. But it's not, when we talk about positive and negatives, we're not talking about a vector. It doesn't have a particular direction. It's just a change. Okay, so, and by the way, kinetic energy is usually referred to kind of like cash, okay? So kinetic energy is like ready to use right now, okay, versus some of the other kinds of energy we're going to talk about in the future. So we'll fill the rest of this out in class. And then if you're trying to calculate the work done by a particular force, it's easiest first, before we get into calculus, to talk about work done by a force that isn't changing in size. Or if they give you an average force, then you can use this formula. So what we're talking about here is a force exerted for a certain displacement. So you might push your bike for a whole block, okay, while you're talking to a friend. So the force that you put on the bike along, that displacement of an entire block, how many meters is that, okay? And then really, because the bike is moving sideways, so here, let me change colors. If we are trying to show, the displacement is along the sidewalk, and then your force might be, if you're pushing down at an angle, then we are going to need to know the cosine of that angle, because the only part of the force that's really productive, that's really helping add to the kinetic energy of this bike, is the part that is parallel to the displacement, okay? And then we can get into why, but one way to explain it is that it's not helpful to push down on the bike. That does not increase its energy. It's not helpful to, throw it up into the air either. What's productive is to push from behind, okay, or pull on the handlebars. And that's the part of the force. We want the horizontal component, basically, this portion, I'll change colors again. Let's try to make this stand out. So we need this, the F cosine theta portion. That's the part of the force that's really helping increase the velocity of the bike. And so that's the part we care about. And that's why we do this as our formula. But your formula sheet is going to list this in a different way. And so they give it as the dot product. And then on the next page, they give the definition of what a dot product is. So when you look this up, you're going to see that it's giving work as the dot product. And then on the next page of your formula sheet, it will give you the math definition of that anything dot product is like those two quantities multiplied together times the cosine of the angle between them. So basically they're like telling you this, but you have to look in two places to figure it out. Okay, so just a reminder for positive versus negative work. Okay, when you're figuring this out, a force is going to do positive work when the force is acting in the same direction as the displacement. A force is going to do negative work if it has a component in the opposite direction. Okay, so like for instance, friction in that case, when I'm pushing the bike, if it's skidding for some reason, if the brakes are on, I don't know, maybe that's not a great example, but then if it's resisting, maybe air resistance is a better one, then that's working against the displacement, so that's doing negative work. And then a force does zero work when it has no component at all in the direction of displacement. So for instance, in that example, normal force is not, it doesn't have any x component. It's all in the vertical component, in the vertical direction. So it's not helping increase the velocity of the bike at all. Okay. And so then when you're looking at the total or net work, you want to look at all the forces, right? So that you can tell what's the net work done on this object. So then we'll be looking together at this question to practice what is the work done by all these forces. Okay, so for now, you might want to jot down what you think these are so that you're ready to talk about this in class. And then also go back to this example, these analogies, and see if you can answer these with your own suggestions. Okay.